Hi everyone, my name is Cédric, and today I'd like to talk about a mathematical framework that helped me greatly in understanding various concepts of mathematics. So a framework that really helped me understand lots of pieces of mathematics, and notably related to computational geometry and computer graphics. I'm quite into computer graphics, but the thing is, a lot of the math around it is really terrible. You have things like homogeneous coordinates, quaternions, projective transformations. You have to do all kinds of intersections between objects like lines, spheres, circles, planes, and when you look up the formulas for these, they're really ugly. And so around the same time, I came across geometric algebra, which after learning a bit about it, I saw as a way to demystify and bring back intuition behind a lot of the mathematics I was seeing. And then as I furthered my learning, I realized it was actually applicable to a whole range of domains, much more than just computer graphics. And so I'd like to introduce you to it a bit today. This is by no means a complete introduction to geometric algebra because the topic is really vast and there's a bit of a steep learning curve. But for me personally, the effort was well worth it in the long run. I will also present a package called SymbolicGA.jl, which is an implementation so that geometric algebra can be used in code for numerical computing, for example. So what is it? So essentially, it's a mathematical framework, as abstract as that sounds. Is also known as the Clifford algebra, for those of you who might know the term, just a specific application of it. So it's nothing new, really. The Clifford algebras have been formalized by William Clifford in 1878, but it went silent for a long time in favor of vector calculus that we all know here. And essentially was sort of renamed geometric algebra when being revived to do physics in modern days. And notably, like in a few areas of physics, and then it expanded to being really useful and of interest to other domains. Just to precise, this is not algebraic geometry. Algebraic geometry is a different thing. So what does geometric algebra bring? Why would you even consider it? First thing for me, the most important is, you often have these formulas with lots of parameters, things that look very low level, especially when you're used to having, nice abstractions in code and so on. And geometric algebra takes another approach to having like all these parameterizations and coordinates and expressions that involve lots of weird expressions. You just have different types of objects and operations between these objects, and you kind of operate really at a more high level. You have fewer details shown to you at once. So you have this expression on the lower right, which might be some valid expression in geometric algebra, which actually represents sort of what these other expressions are representing, just in a different way. And I find it more readable, personally. It's also a common language for various branches of mathematics and physics. And when you talk this one language, when you learn it, you can actually generalize your knowledge to quite a few branches. I personally learned about space-time physics just because I learned about geometric algebra, and then there's a really nice description of space-time physics in terms of geometric algebra. It's also a way to generalize rotations. So in 2D, 3D, you have like complex numbers, quaternions. With geometric algebra, you can also express rotations on higher dimensions, like 4D, 5D, ND, and all with kind of the same formulas you would get for 2D and 3D, which is really neat. And last, it's really easy with it to get the big picture and to get intuition behind all of the math that you're doing. Again, greatly in part because you have this lower symbolic complexity, but also because at every stage, every sub-expression in your algebra actually represents something meaningful. Now, what is it concretely used for? So there are a bunch of applications. First one is to represent geometric entities, like if you want to represent points, lines, circles, spheres, planes. And as I mentioned, sometimes you have to take intersections of them. You might join two lines or do things like that. You can do it very easily in geometric algebra, and it shines really for that. You can also express things like orthogonal transformations, which are mainly the reflections and rotations in Euclidean spaces. But when you go to non-Euclidean spaces, you can get other types of transformations. So things like Euclidean transformations, if you go into projective spaces, or conformal transformations with things like inversion, like spherical inversions when you go into conformal spaces. And in space-time physics, you can actually express Lorentz transformations, for those of you who might be familiar with the term, just as a simple rotation, really. You can also, with that, model non-Euclidean spaces if you, for some reason, want to know what spherical spaces or hyperbolic spaces are. It's actually quite straightforward to understand with that framework. You can also do some calculus on it. Though personally, I haven't done much, but people have been using it to do, for example, differential geometry. And actually, it includes a generalization of differential forms, which is really in a more elegant and intuitive way. And personally, I learned about differential geometry just because, again, I learned about geometric algebra, and the description of differential geometry in terms of that language was actually very straightforward. And it was really, really useful for that. In terms of the different domains of application, I would highlight robotics and computer vision. Like anything that has rigid body transformations that need to be represented. You have things like dual quaternions, which maybe you're familiar with. Essentially, geometric algebra allows you to express those as just a tiny subset of the algebra. You can also do computational geometry, as I mentioned, to do any kind of geometric queries between objects or transformations in 3D space. Game engines have also used it. You can do things like 4D rotations. There's actually a game that did that using geometric algebra because it was just way easier. And non-Euclidean world also, if you are into that, why not? You can also, as I mentioned, do space-time physics with a space-time algebra, which has known a lot of success. You also have electromagnetism that is easier to do, both the classical and relativistic formulations, where notably you can reduce all the four Maxwell's equations into one, with an invertible differential operator that leads to really great ways to compute an electromagnetic field. All right, so now let's dive a bit into what it is. Presented what it might be useful for, but let's try to understand how it works. So I like to think of it as, it's kind of a language or framework, but really the starting point is first you have a vector space. Let's say you are in R2 or R3. You pick that, and you're going to add a bunch of objects into it, and actually into another space. So you're going to create a new space where you have the vectors, the scalars, but also different kinds of objects. And then you're going to add operators which, when combined, actually express geometrically meaningful transformations, which I will cover in a moment. So for the types of objects you might have, so we have the vectors and scalars. Here is an example. If you wrap R3, for example, you have also objects called bivectors, trivectors. These things that are generalized to k vectors. These things are essentially products of vectors. So a bivector is sort of an oriented area, a trivector an oriented volume, and k vector an oriented k volume. Just a special mention for the last object, or the last graded object in that space, which is often referred to as the pseudoscalar or anti-scalar, just because it's some kind of object that has mainly one component, and that has duality. When viewed from a duality perspective, it actually looks like a scalar. So how do we go about embedding a vector into that space and to generate these other types of objects? So let's say you have some object x, so in your vector space, so it's just a flat list of coordinates. So first we're going to change from a list of coordinates into actually explicit components behind specific basis vectors. Just because there are different types of objects, and if you have 3 coordinates to describe something, it might be for a vector, but also for another object. Then we're going to introduce an operator called the exterior operator that has essentially the effect of joining its operands into a higher dimensional subspace. So here we're going to join x and y. And you might recognize the formula a bit. What we get is sort of cross products, but not exactly. Because with a cross product, you typically get a normal, so just a vector. Here we actually get a bivector. So something that really represents the planes spanned by x and y in a way. You can also add one more operand and get a trivector, for example. And here you might recognize that we have the expression of a 3x3 matrix determinant, which is not a coincidence. And actually, you can compute any matrix determinant just with the exterior product between vectors. So this is a first geometric operator, so an operator that actually carries geometrically meaningful transformations. It's also called the outer product. In geometric algebra, unfortunately, notation is there is no really agreed upon notation for everything, and so sometimes you find different names or different notations for the same things. And this exterior product is defined in terms of a more fundamental product, which I will introduce shortly, called the geometric product. And so here, say we have a k vector A and S vector B. Taking the exterior product of it is just taking you would say the components that correspond to the k plus S dimensional elements that is returned by the geometric product, which returns also other elements. There's another product called the interior product or inner product, which this time does not really represent joining objects, but more like projecting objects onto other objects, or also to express measurements like norms and distances, which is defined very similarly. The geometric product is again really the fundamental operator. You just take a different part of the result. So this is the last bit of math, bear with me. So here we define the geometric product. Essentially, we say how to compute it because it's actually axiomatically defined. It's not like f of x equals x plus something. You just have a set of mathematical rules, axioms. When you work them a bit, you actually end up with a set of rules to say how you need to carry out the computation. And so the first rule is that it is distributive. So essentially, if you have a sum of basis vectors, like any general vector, you can just distribute the geometric product to each of these basis vectors that it is made of. If you have a scalar, you can just put it in front, so that then you really only need to consider the geometric product between basis vectors, or basis k vectors more generally. Let's see what it is with how it is computed with an example. So here, let's say we have E1 to 3, a basis trivector, and we take the geometric product with beta E1. So essentially just a vector, one vector. So first, we can put the beta just on the front. We don't care about it. We just need to consider the geometric product of what is inside. And then we're going to, we have a rule that says we can permute these indices if we apply a minus sign. So we can apply two permutations here so that the ones are facing each other, which we can then group. We can collapse the geometric product because the definition of EIJK as a basis trivector, for example, is just EI product EJ product EK. And here we end up with two indices that are repeated. And there is an axiom that says, or a rule that says, well, here that it actually can be simplified to just a scalar. And so this scalar is actually depends on how you define the space in which you're operating. But it's essentially just a scalar that is standardly -1, 0, or 1. So here we can say maybe we can set that to 1. And so we end up with beta E2, 3. And so if you know how to apply these rules, you can apply the geometric product between arbitrary elements of that space, be it a sum of a scalar and a trivector with a product that has on the right-hand side a vector. You can just distribute everything, carry these rules, and you get the result. One last thing that is quite nice is that for one vectors, the geometric product has actually a really neat formula, or rather description, which actually motivated this wedge dot notation, which is quite often replaced with just a standard multiplication operator. It's actually incredibly hard to type in LaTeX because LaTeX does not support that. But here in this case, for one vectors, it simplifies to the sum of the interior product and exterior product. But that's just for one vectors. Generally speaking, a geometric product might split a lot of different types of objects, not just 2, can be 3, 4, 5, that depends. All right, so now let's jump into how we can actually use that language in code. If you do some numerical computing, you probably want to be applying these operators so that you can express the logic of whatever algorithm you have at hand. So there are two main ways of implementing geometric algebra. One might be to just tackle that as another programming problem. So obviously we have different types of objects. Okay, let's make structs for types of these. Operators look awfully like functions. So we're going to make functions. The geometric product is the main one. All the operators are derived from it. So probably you just focus your implementations on types and the geometric product. And that's all and fine. There's actually another way we can go about it, which is to say, well, we don't really need to represent like objects that live in these abstract spaces. we can just say, well, get me the numerical expression that corresponds to taking the product between this and that. So essentially, you just generate a code expression based on the inputs algebraic expression that you provide. I will actually choose the second way of doing things, which might not feel so intuitive, but I will show that actually you have nice advantages of using that, which is a much more looser term for a looser way of implementing geometric algebra. And first, I'd like to claim something, or rather, this is my opinion, but for me, when I use geometric algebra, it's not really about what to represent in code. I don't really care about representing bivectors or trivectors, just that when I have some logic to express, I can use these objects and these operators to carry out this logic. So I want to be able to use these kinds of expressions, which probably don't talk to you at all, but after some practice with geometric algebra, you can recognize that some of these carry meaningful transformations, and it's sort of a nice and intuitive language. So then we might think, okay, so it's just a language. So I guess some kind of domain-specific language. Well, turns out, yeah, we can look at this way. Look at it this way. So let's see what it would take, because actually there are quite a few steps, and it's a bit involved. Just going from one input expression to all the generated code. But let's say we have this expression where we want to execute the geometric algebra expression over a space parameterized by a signature of 2, saying essentially here that we just take R2 as our base space, and all of the basis vectors squared to 1. Quite straightforward space. We're going to put the result into a tuple. So we can do any computations in between, scalar computations, but then just put a tuple at the end. And then we have our actual expression, which is defined with some basic syntactic rules. Bindings, so ways to describe, for example, operators. Here we have this Unicode operator, wedge dot operator. You could potentially use a different binding for that. And we have also these sort of type annotations, but with numbers, which actually inform the implementation that you can consider X and Y to be one grade elements, one vectors, so just vectors. Then once you have parsed all that into a more structured representation, you can actually simplify everything and apply the rules that I just mentioned. And so you're going to essentially distribute everything. All of the geometric products that you will see, you will distribute them and end up with a vast sum of different terms. So then, because a fully distributed expression is not really efficient to compute, you typically want to have some kind of refactorization step, if you can, and try to deduplicate some of the computations, notably if you have common sub-expressions. Don't need to compute them twice. If they appear twice, compute it once, take the results for the second one. And then you end up generating code for it. So actually, the code that I showed earlier, we're just implementing that operation, which actually produces here a scalar and a bivector. And so to implement all of this in code, I made a package called SymbolicGA.jl, which I find quite practical in a sense that it really allows for optimal runtime performance, theoretically optimal, because you have really full control of the expression that is generated. I also wanted to support arbitrarily defined user-defined geometric spaces. So you can have standard geometric algebras over R2, R3, but you can have really vastly exotic spaces if you like. Also, one point of interest was that it would be really great if we could easily interface with the code and say, well, you only just need this one line in that obscure language to express your computation, but then you don't leak any objects. Like you don't need to leak bivectors or trivectors into any user code. So here you can say we have 2 lines, maybe from some computational geometry package. We can consider them as bivectors. So this is what we tell with these great annotations. And then we just put the results inside a point, which again might be defined by this library. So then really you just have one line of it. There's actually a nice side effect that came from processing an expression at macro expansion time, is that you can really have any notation that you like. Because we just have a macro that then can do arbitrary stuff to the input expressions you give it. And if you parameterize this macro such that you have bindings and you can have sort of basic functions, then you can say, for example, oh, well, let's use this multiplication operator to represent the geometric product, which is some kind of built-in operator, just with ASCII letters. And say, OK, I don't want your wedge dot product, maybe. And then you can actually do that. And that's just because you operate on expressions, which is pretty neat. All right, so now I'll get to conclude, because I don't have so much time. So I presented geometric algebra as really a mathematical language and framework where you can essentially bridge a few branches of mathematics and physics, and which gets you a greater intuition when you have acquired some understanding of the language. I have to warn, though, there is a steep learning curve, but you really get a lot out of it. And then the way that it works, it's really you take some base vector space, you add more mathematical objects to it, and then you define with axioms operators that, when carried out, have a geometrical interpretation. And then last, this language, which really is some kind of mathematical language, can be used, so first it can be used just to carry calculus. You don't need to have anything numerical computing related, but you can use it in a performant and flexible manner just by making it some domain-specific language and leveraging the metaprogramming capabilities that the Julia language provides. All right, thank you for your attention.
Thank you very much, Cédric. Do we have questions for Cédric? Please.
Thanks for the. Oh. Thank you for the clear introduction to this topic. I guess I have two questions. First is, are there resources that you found particularly useful in learning this?
Yeah, there are a bunch of resources. I actually put a few of them in the documentation of this package, so you can look them up. There are essentially a few books, but again, you might have different notations, different interpretations, different perspectives. So I wouldn't recommend just one particular book. You can dive into David Heston's reference book about geometric algebra with all the axioms really rigorously defined with a presentation of the differential geometry, but that is not really entry-level material. But actually, you can learn a great deal by reading it. But you have a lot of other more approachable resources, yeah.
Great, thank you. Second question is, I've seen a few different geometric algebra packages, and I wondered if you could give a comparison of those to your package.
Yeah. So essentially, first, I'd like to say that there is no single geometric algebra package that should win over the others. Essentially, different packages hit different trade-offs. As far as I'm aware, this package is the only one that does geometric algebra at micro-expansion time using metaprogramming. Most of the other packages, they would typically have more straightforward implementation for different types of objects. And there are a few, yeah, definitely a few of them, one of which is going to be presented by Chris Doran just after the session.
Yeah, quick. Okay. Yeah, thanks for a nice talk. So my question is, if you, for example, use the expression for rotation, and then compared it with the code generated with sort of maybe the quaternion rotations or matrix-based rotations, I was just curious, does it basically then give you the same expression as quaternion rotations?
Yeah, for quaternions, yes, definitely, because they're really the same types of objects that you manipulate, just that it's for a specific space, but you can recover exactly quaternions. And for matrices, yeah, you have at the end really the same expressions, I believe. Yeah.
No, I was just curious, in your version, when you type in the geometric algebra formula for rotations,
yes.
What do you get at the end? What algorithm it sort of produces?
Well, it's really a bunch of scalar operations, which is not so readable,
Okay.
but it should do the same thing.
Okay, thank you.